Stanford University.
Good afternoon, everyone. Welcome to the last section of Friday's CS 193P. We've got a couple guys, Adam and Nick from LinkedIn, to talk about some development on the iPhone, so I'm going to hand it off.
Great, thanks, Paul. So hi, everyone. My name is Adam Nash. I'm the lead for platform and search products at LinkedIn. I'm here with Nick, who's our lead engineer on the iPhone. We thought we'd come in today and talk a little bit about our practical experience building our iPhone application. It's an amazingly important initiative for us at LinkedIn, and we've learned a lot along the way, and we thought it would be a benefit to the students in the class to see some real experience with technologies like CoreData and, of course, GameKit, which we actually use for something that's very much not a game. So I'm going to start off with just some basic background on the LinkedIn application and kind of where we are today. Then I'm going to hand it off to Nick, and Nick's going to walk through some of those experiences with both CoreData and GameKit. So, LinkedIn Mobile is pretty simple. For those of you not familiar with LinkedIn, it's the world's largest professional networking website. We basically are the social media platform for business people to get things done. We have over 60 million members. Our mission as a company is to connect the world's professionals to make them more productive and successful. The reason that's so important for us to be live on mobile is because we want that to be true anytime, anywhere, right? Professionals are the type of people who aren't at their desks all the time. They go from place to place. They go to meetings. They visit customers, clients, et cetera. And we want them to have the power of LinkedIn anywhere they go. And so obviously our mobile products are incredibly important to that and to our audience. For LinkedIn for iPhone has been actually one of our first mobile products and certainly our most successful. We actually, right after the iPhone shipped, we're a local company, obviously. It kind of tore through the company, right? Everyone got iPhones. We figured out how to make our internal systems work with it. Pretty soon after, we'd done a custom version of our m.linkedin.com website for the iPhone. And then soon after the native platform launched in June 2008, we launched our first native client. And since then, we've done a couple iterations. Actually, one of the iterations we did late last summer, which launched in October, was actually done by a student in CS 193P who actually interned with us over the summer. And then, of course, we did a complete rebuild and redesign of the app and launched it December 28th. And that's what you'd see in the App Store today, is LinkedIn for iPhone 3.0. There's two areas of technical focus, as I mentioned at the beginning, that we're going to talk about today. We're going to talk about CoreData and the massive enhancements in performance with some key learnings about when to use it and how to use it. And then, of course, GameKit. We thought it was particularly interesting that GameKit was a technology not just for use for gaming or those typical applications, but also any time that you need to manage an interaction between people who are in person. So with that, I'm going to hand it off to Nick, who's going to start off with a discussion of CoreData.
Oh, thank you.
Oh, I think you have a mic.
Yeah, I'm all wired up, I think. So I'm Nick Gillette. I'm the iPhone lead at LinkedIn, and I sort of cut my teeth at the company working on 3.0. There were a few sort of key lessons that we took away from that endeavor around both performance and then also kind of how you get two devices to interact with each other and what it means to be in a room full of people with an iPhone. I'll go over some of the lessons that we took away from that experience. The facts are that when we started the endeavor, we had some interesting performance issues. We had some performance profile that we didn't really feel provided like an optimal experience on the device. When you downloaded Adam's connections, actually, it took about a minute to a minute and a half for the device to really get all that wire data, parse through it, and then also serve it up in a display to the user, basically a simple table view. Table views in the iPhone are designed to perform, so it was very interesting to us that we weren't. That we didn't feel that we had a snappy UI, and that we didn't feel that, even with such a large data set, that we didn't feel that we were still giving the user the experience that we wanted to. To address this, we sort of started to aggressively look at caching. We started looking at ways that we can keep data local on the phone to the user and ways that we can give them the experience that we want, which is that their data is always available and that it's usable whenever they want to have it. 4.5 megabytes on the iPhone disk cache didn't give us the load time that we wanted. We just couldn't get that data out of flash memory fast enough. And so we started investigating ways that we could take that file size down. CoreData helped us with that. And we got a lot more performance with a lot less overhead. Some of the things that we took away from that were, versus our plist storage cache, we basically archived our member objects into a plist file and then saved that to disk. With CoreData, we dropped 90% of that disk size. We went from 4.5 megabytes to about 350 kilobytes. So you're talking a significant reduction in storage size, right? And this is using a SQLite backend, so it's searchable and you can sort it and all that. We also noticed that at serialization time, when this data comes across the wire and when we were actually working with it, when we have NS dictionaries from JSON that we were putting into our CoreData objects, we required a lot less overhead. We created fewer objects, we required fewer strings and fewer dictionaries, and we went down by about 60% of the number of objects that we would have open in memory at any one time. Now, this is a side effect of not only our serialization paradigm, which I'll talk through a little bit in a minute, but also kind of how CoreData actually deals with object serialization and saving and storing into its data store. What we did was we actually tried to sort of walk away from the complexities of serialization in our app. A lot of applications will have a pretty tightly coupled serialization paradigm whereby they actually take a dictionary that's been serialized from JSON and then grab raw objects out of that. It's not type safe. Dictionaries will return you an object, and depending on your JSON serializer, you could be getting an object of any type, a string, a number, a date, depending on how well your serializer actually works. And it also doesn't ensure that a value is always validly initialized. And by that I mean that if the key that you're looking for isn't found in the dictionary, it might get set to null. But if you have some if conditions checking for that key, then your variable won't be initialized, as you see kind of at the third line there. Our code was actually riddled with stuff like this, and we used a very tightly coupled serialization model, which means that as you can see, the keys that are in the serialized dictionary are actually hard-coded into the application. So if we have two different server calls, one that returns a member object with the first name key as like member underscore first name, we would have to write different serialization code for a call that returned it with just first name. And this leads to a lot of code bloat. You really don't have you have multiple code baths that kind of do the same thing, and some that could be eliminated for the sake of performance. Our sort of code bloat actually led us to a huge problem when it came to validating our application and testing it. What we had a member object class, one of the files that you see listed here, which had about 400 lines of serialization code in it. That's a big set of code to actually validate and test. And it presents a huge challenge when you're looking at iteration and trying to build on top of that. With CoreData, we actually moved all of our code outside of the data, sort of the in-memory object representation, and into kind of pure classes or categories, so that there was no serialization code directly tied to the object model anymore. We also reduced our serialization code by a factor of 3. So we went from about 1,500 lines of serialization code to about 500, give or take. And the way we did that is by actually taking the serialization responsibility away from the data model. And so with that big of a reduction in code and the code footprint, you end up with a much more testable application because you have repeated code paths that are used to serialize every single object. The challenge is actually in figuring out a way to model these objects so that you can implement a paradigm like this. And CoreData actually solved that problem for us. Your first step with data serialization is that you generally start looking at the objects that are coming back from the server. And one good way that you can work with them is to build a category on top of your object model to actually handle the serialization for you. So you have some category that is basically built on top of your NS managed object class implementation. And that category knows how to take a dictionary and turn it into something that you can use. And it also knows how to take an object and turn it into something you can send back across the wire. This is a good start because it puts all of this code in one place, and it's also not tied directly to the files that CoreData generates. So when you regenerate your class files, you don't have to worry about destroying any of this code. The problem is that it doesn't solve the coupling. For that, you need to look at a little bit more complicated paradigm, something that's called aspect-oriented programming, which is where you have an object model and you tie individual concerns to that object model via either config or in-application hooks. What we actually do is we have a general class which is responsible for filling all of our model objects. So that includes things like our member objects, our network updates, our emails and messages. and any other object that you might have in the application. It uses a variety of config to know how to serialize these objects. But the basics of it are that you parse through the entity description in CoreData, see what keys are in that entity description, and then read some config to discover how they map to the keys in the response dictionary if it's not one-to-one. You then have to deal with type coercion. And most JSON serializers will attempt to do some of this for you. However, whether or not they do it correctly is open for debate. One of the interesting cases that we have on LinkedIn is that some of our members put their phone number as their first or last name. It parses directly to an integer in most cases, sometimes a double or a long. But that presented an interesting challenge when we were serializing the first name into a string. And that's not a string. The JSON parser will parse it out as an integer. And in your code path, when you try to ask that member variable for its length, it will throw an exception because NNS number doesn't know anything about length. So you have to do some amount of coercion to make sure that the data type that your entity expects is actually the data type that it gets across the wire. And for that, we use NS-value transformers. These are hooked in via config, and they basically say for a given key path in the serialized dictionary, I'm expecting a type to come back of like an integer or a string or a date, and then we'll instantiate the correct transformer and ask it to transform this value for us to make sure that it comes out to whatever we expect. So even if the JSON serializer parses it as a number, we can turn it back into a string at that time, or vice versa. This is our member object as it lives in CoreData. It has a lot of properties and relationships that are hooked up to it. It's one of the sort of core central objects in our graph. And this is kind of the configuration that we use to drive it. The interesting thing here is that we have a couple of different things going on. At the top, there are hooks that we use to identify the primary key value and where that lives in the response dictionary so that we can uniquely locate an object in our CoreData store. That will allow us to do deduping at response time. So for network updates, we'll get a member object back with those as the user that generated that update. If that user is already in our store, we don't want to overwrite their possibly complete member object with the limited set that comes back in the network update. We also have a set of aliases that map the response dictionary keys to the keys in the CoreData store. This is important because it basically allows us to say, all right, in one response dictionary we have the key first name, and the other we have the key member underscore first name. And finally, we have what are called concerns, and this is sort of the real aspect-oriented part of the CoreData storage system. These allow us to do operations on the entities as they come back that can't be mapped out in CoreData. For example, you don't want to have a dynamic property that generates a user's initial for their first name. The reason is that every time you render a table cell, you'll have to regenerate that property dynamically by concatenating the string of their first name. With a concern, we can do it at serialization time. If your member views that individual member object more than once, then doing it at serialization and archiving it into the CoreData store pays off performance-wise. Otherwise, you have to redo it every time they view that object. Connections are kind of a central part of our application, so we expect that the average member will view their connections probably on the order of hundreds of times before we actually wipe out the caching store. So finally, we have these concerns, and these are configuration-driven objects that allow us to do these operations. A lot of them use NS-value transformers. Some of them are more complex. They can create entities or actually fill relationships on the other side if they need to. This is one example. It just fetches an initial transformer, which simply takes the first character from the string out of the config. And so that's how we got down to about a third of our code footprint for serialization. Some common CoreData sort of programming mistakes that a lot of people make when they first start working with it are the standard template for a CoreData application will actually give you an NS-managed object context that lives in your app delegate. The app delegate is one of the most accessed pieces in any iPhone application, so the odds that it's going to be thread safe are very low. You should never share a persistent store coordinator or, even worse, a managed object context or any of its objects between a thread or two separate threads. And so this tends to be kind of one of the first points that applications start to fall apart. A lot of applications think that having a shared persistent store coordinator that talks to their storage system gives them concurrency. The problem is that it actually doesn't. If you share a persistent store coordinator between multiple threads, then your application isn't concurrent. The store will be operated on and blocked on due to optimistic locking for multiple threads at the same time, while other threads are trying or waiting for operations to happen. So if you want true concurrency and you want true write-through performance, then you need to have multiple persistent store coordinators. There isn't much overhead to having multiple, so a lot of times it's better to go with more than less. If you have questions about which one is right, then you can instantiate manage object context with a shared one for, say, a view controller or some other pieces of shared code. A lot of programmers also tend to assume that their view controllers are single-threaded. And the truth is that only the UI delegate methods and the methods directly called by UIKit will be single-threaded in a view controller. So we often see that action calls or hooks that people have via their own delegates on view controllers get into threading problems. And this causes a huge issue if you have a shared manage object context for an individual view controller, when you use like a fetched results controller or even some more complex setups. Another big performance hit for CoreData is when you do actual class inheritance. So for example, if you had some class which inherited from a member object, maybe you had a special class of member like a pro user or something, then you wouldn't want those to be modeled in your object graph in CoreData. You'd actually want them to be two separate entities, because following up that inheritance tree when CoreData faults on the key pass is very, very expensive. Finally, this is in the documentation, but it's worth stating again, don't store media in your CoreData store. Any binary large object will absolutely kill your performance. It's expensive to fetch, it's expensive to store, and it causes a lot of problems. And last but not least, manual serialization. It's what I talked about in the beginning, is that hard coding key pass is not really a scalable way to serialize your data objects. If you can at all, you're building anything larger than sort of a small scale application, you really need to be a bit more dynamic and a bit more flexible about it. That's kind of all for CoreData. Is there any catch-up questions or anything I can go through again? Sure.
So for how long do you store the data in the CoreData?
That
you have to refresh it. So.
That depends on your implementation. We don't actually ever have to refresh our data unless we detect that it's gone stale. So we have APIs that allow us to detect whether or not a member's profile has changed, whether or not someone has added a new connection or removed one. And so using those APIs, we can actually eliminate objects or update objects in the cache. That obviously changes if you don't have an update policy. If you have a replacement policy, then your objects may become invalid based on how you replace them. A couple notes on the managed object context in general. You should fetch these kind of as you need them. There's no harm to having multiple in memory. They're very lightweight. It's the objects that live inside them that really take up the actual physical memory on a device. So if you're fetching 10,000 objects into more than one managed object context, you might want to rethink how your user is using your data. It's unlikely in that case that they're actually getting a usable interaction out of having all those objects in memory, so you should probably revisit that. But for true concurrency, again, each managed object context should point to its own persistent store coordinator. If you have a lot floating around in memory, then they can obviously share one. But for real concurrency, they should each have their own. In our application, we actually do this using a couple of different paradigms. We create persistent store coordinators on the fly, but we also have a facility for sharing them between multiple managed object contexts. They're easy enough to create, and you can sort of customize them as you need them for different persistent stores, et cetera. And the managed object contexts themselves, it's good to have sort of a static singleton method, maybe a category on a managed object, to vend back a new context for anyone that needs it. This way you encapsulate all the instantiation code in a very local code path that you can test, and then also hopefully detect any bugs or issues in pretty quickly. Again, with threading, a couple of things that'll kill you. The first thing is performing any kind of fetch on the main thread, which is the UI thread, is a really terrible idea. Even if you have a SQLite storage that is really fast, it's really hard to provide a snappy user interface when you're blocking the main thread for any kind of operation. Some usual do's on background threads, you usually want to put things like raw fetches. For the first time you're fetching objects into a context, you usually want to do that on its own thread. Once those objects have faulted against the store, then you can usually instantiate another manage object context and then pass out the object IDs of the ones that you used in the fetch. This comes in handy when you're doing complex sorting and searching fetches, things that have to search over multiple fields or sort multiple fields. You can then pass those IDs onto a thread to display to the user. Merging objects into the store should absolutely always be done on a background thread. And the reason for that is that optimistic locking can block your main thread and cause your UI to hang. So big note is don't ever block the main thread. And in your application, if you have a lot of serialization going on like we do in ours, you must absolutely pay attention to save notifications. CoreData does a really good job of letting you know across the application which objects have been modified and which ones haven't. And when an object is modified, if you're paying attention to it, then you absolutely should refresh it. Otherwise, optimistic locking is going to be the bane of your existence when you try to save it. There's also facilities in CoreData for merging these objects. Once you detected that they've changed, you can set a merge policy to tell it, yes, you should overwrite the values, or no, you should try to merge the values, etc. Again, don't ever perform a selector on the main thread. Please do just attach a new thread in the background for any complex operations. Lastly, I'll cover a little bit of our challenges with GameKit. Our interaction with GameKit is not too involved, but it needs to be really high rate because of how we want users to use it. The basic UI flow is that you can open a screen called In Person in the iPhone application, and it will actively scan for any other LinkedIn apps around you that are running in person. When it finds some, it will pull them up on the screen and display the list of users that you can connect to. This is one way that we encourage users to share their LinkedIn information actively with the people around them. And we see most of its adoption at conferences, but the UI is such that when you sit down with somebody in a meeting or in a conference, you can really interact with them quickly. And in order to do that with GameKit, there's some paradigms that you kind of have to avoid. One is the device choosing step of the typical GameKit UI. That's a huge blocker if the person has to go through and kind of click on what device they want. Our flow is more that they can kind of pick any device around them, and then they can choose how to interact with that device. The big points with GameKit are usually kind of the typical ones that you see in the documentation. You shouldn't engineer for Wi-Fi unless you're going to restrict your application to Wi-Fi, because when it goes on Bluetooth, it's likely that it will fail. The bandwidth and the reliability of Bluetooth are so significantly smaller than with Wi-Fi that if you do all your testing on Wi-Fi and you do all your engineering on Wi-Fi, you're either going to be transmitting too much data or you're not going to have enough reliability for the packets to actually get across. The other big thing is focus on sort of the interaction you want people to have with your GameKit interface and not on the data that you need to drive it. That will lead you usually to using sort of just enough data to actually drive that interaction. If you use too much data, odds are that the user isn't going to be able to perform the action that they want at the rate that they want, because they're going to have to sort through a complex user experience. The big crux, of course, is sending media and large files. This almost always fails over Bluetooth. From other developers that I've talked to, trying to send anything more than a couple of kilobytes over Bluetooth, even with the reliable hook, is a way to absolutely kill your application's performance and drain the battery on an iPhone. The other key point is to require the user to act only when they absolutely have to. For us, that means that as developers, we'll take the responsibility for finding the devices around them, and we can get them to the point where they can act on those devices that we found, i.e. connect to other users, share some information, but we won't encourage them to take any action until that's the one that they can perform. These are all the properties of our member object, and these are the set that we actually send across for GameKit. It ends up being about 200 bytes of data, whereas a typical member object can occupy anywhere from 5 to 10 kilobytes of wire space. It's a significant reduction, and it's one that actually allows us to deliver a really fast, snappy user experience on GameKit, because we're not waiting for data to load into the device. Almost all of our interactions are on Bluetooth because most of our users are away from their normal Wi-Fi network or in an environment where Wi-Fi is not pervasive, like certain conferences or a meeting room. And we achieve that by simply accepting GameKit requests for the user. When a device wants to connect, our application will actually just accept that connection request for them and then send a small set of information. It's a very lightweight ping request to the other device so that it can display sort of the member's name, where they're from, and then the picture. It's important to note that that picture is not sent across on the Bluetooth connection because of its size. It's about 4 to 8 kilobytes. The other phone will actually load that over its data connection. That was one of our core challenges with GameKit, was kind of that, we have some data that can be large, but it's actually easier and faster, it turns out, for the phone to go out over the wire and fetch that data as opposed to having us send it over Bluetooth. With Wi-Fi, it's a little bit of a trade-off because you have so much more bandwidth and it's a much more reliable network to deal with. But with Bluetooth, you definitely want to be able to get the large sets of data from another source. And lastly, a couple of things to really focus on when you're doing your iPhone development. The most important is obviously the visual representation of whatever complex data you have. That's kind of what the iPhone is all about. Unit testing is a huge plus. If you have time for it, write them up front. If you don't, go back and write them, because they will save you a ton of time debugging your code. And if you find a bug, the best way to prove that that bug isn't going to come up in the future is to write a unit test for it. Finally, thread safety. I don't think we've been bitten by more bugs this year than with thread safety. And it's not so much that you can't engineer your application to work in a single-threaded environment, but with threading, timing is always an issue. And the more you focus on keeping your threading in an isolated environment and making sure that the objects that you're dealing with are thread safe, the more time you'll save on debugging those interactions and those problems.
For more, please visit us at stanford.edu.